Welcome back to Tokenization from Scratch. We have a working tokenizer that turns text into a list of integer IDs. But what actually happens to those IDs inside a model, and how big should the vocabulary even be? In this episode, we connect tokens to the neural network, weigh the real cost of vocabulary size, and finally solve the famous puzzle: why a state-of-the-art model can't count the R's in strawberry. In the last episode, we registered special tokens like end of text and the chat turn markers above our learned vocabulary. So our vocabulary is now 3 layers: the base byte tokens, the merges we learned, and the special tokens on top. Each one maps to a single integer ID. Today we ask the deeper questions: what does an ID actually mean to the model, and how does the size of this vocabulary affect cost, speed, and even what the model can reason about? Choosing a vocabulary size is a balancing act with no free lunch. A small vocabulary keeps the embedding table tiny, but every sentence becomes a long list of tokens, and attention cost grows with the square of the length. A large vocabulary makes sequences short and snappy, but the embedding table balloons, eating memory, and rare tokens get so few examples that the model struggles to learn good vectors for them. Real models land in the middle, usually tens of thousands of tokens. Here's the tension drawn out. On the left, a small vocabulary means a tiny table but many tokens per sentence. On the right, a large vocabulary shortens the sequence but the table grows enormous. Neither extreme is good. The sweet spot is a vocabulary big enough to keep sequences short, yet small enough to keep the table affordable and well-trained. Let's make the cost concrete. The embedding table has 1 row per token, each row a vector of some width, here 768. So its parameter count is simply vocabulary size times width. As we scale the vocabulary, watch the table grow, because every single token we add is an entire new row of numbers the model must store and learn. And there it is. GPT-2's roughly 50,000 token vocabulary already costs nearly 40 million parameters just for the input table. Push to 200,000 tokens, and you are past 150 million before the model has learned a single thing about language. That's why vocabulary size is a budget decision, not an afterthought. Here's the bridge from tokenization into the model itself. An embedding is nothing more than a lookup table, 1 row of learnable numbers per token ID. We make one with 320 rows, each 8 numbers wide. When we feed it the IDs for our strawberry tokens, it simply gathers those rows. No arithmetic on the ID, the integer is purely a row address. If you want to follow along, this is the only slide that needs pip install torch. Running it confirms the picture. The table is 320 by 8. We asked for 3 IDs, so we got 3 rows back, each 8 numbers wide. ID 266 just picked out its row. That vector is what the model actually learns and reasons over. The token ID is an index, the meaning lives in the row. Visually, this is the whole handoff. The tokenizer produces an integer ID. That integer is read as a row number into the embedding table, and the matching row, a vector of learnable numbers, comes out. That vector is what flows into the rest of the network. Tokenization ends exactly here, and the model's learning begins. Here's a consequence most people never notice: the same meaning can cost very different numbers of tokens across languages. Tokenizers are trained mostly on English text, so English packs efficiently while other languages fragment into more pieces. We can see the root of it without any library at all just by counting UTF-8 bytes, the floor byte level tokenizer starts from. The same phrase, I love learning, costs 15 bytes in English but 48 in Hindi because each Devanagari character is 3 UTF-8 bytes. Japanese is shorter in characters yet 3 times the bytes. A byte-level tokenizer inherits this gap directly. That means non-English users often pay more compute and more money for the very same sentence, a real fairness and cost issue baked into the vocabulary. Finally, the payoff. Let's run the famous word through the very tokenizer we built in earlier episodes and actually look at what comes out. We encode strawberry, decode each ID back to its text piece, and count the RS the model can see inside each individual token. This one print statement explains a quirk that has embarrassed every major model. There it is. Strawberry isn't 10 letters to the model, it's 3 tokens, straw, bear, and Y. The individual letters are gone, fused into chunks before the model ever sees them. To answer how many RS, the model would have to remember that the straw token hides 1 R and the bear token hides 2 facts that never appear in its input. It's not bad at counting, it literally cannot see the letters. The vocabulary erased them. See the diagram for the full picture. Side by side, you see 10 letters with 3 RS, the model sees 3 opaque token IDs. Every famous counting failure traces back to exactly this. Tokenization fuses characters into chunks, so per-letter questions are asking about information that was discarded at the very first step. Let's recap. Vocabulary size trades sequence length against the size of the embedding table. A token ID is just a row index into that table. The model's understanding lives in the row, not the number. The same meaning can cost very different token counts across languages, and because tokens fuse letters together, the model genuinely cannot see individual characters, which is the whole strawberry mystery. Next time we put our hand-built tokenizer up against the real ones, TikTok, Hugging Face, and Sentence Piece. See you there.